He has served to the community as the director of the RAISE program, which is the Russian-American Initiative on Shelf-Land Environments in the Arctic. It was an NSF-sponsored panel. He's been a member of the Arctic Climate System Study and Climate and Cryosphere, the CLIC group, Numerical Experimentation Group. And he has many other items on his bio here. Vlad's been very active, but I'll just also mention that he has also served the scientific community as a member of the National Academy's Designing an Arctic Observation Network publication. So we're fortunate to have Vlad here to talk about the state and fate of permafrost in a warming world. Thank you.
Thank you very much. Mary, thank you very much for inviting me this very important, prestigious forum. And it's doesn't work. Hello, hello. Yes, this one work. Just before I start, actually, I'm not anymore president, so but it's okay. It happened sometimes. So actually, go ahead, keep going. Okay. So in this presentation, I would like to bring some questions related to permafrost and permafrost changes, which this presentation was prepared in collaboration with many permafrost scientists, not only from the Geophysical Institute and University of Alaska Fairbanks, but also with many scientists around the Northern Hemisphere who materials I used and from my collaborators. So I think before I start, I would like to introduce one more category in these questions about what we know, what we don't know. So I think there is another category is we think we know, but in reality we don't know. And I think permafrost is pretty much in many aspects is from this category. And I hope this statement will not ruin my career. So a couple of words introductory. So permafrost is by definition is any soil, rocks, or any earth material which is temperature below 0 degrees Celsius for 2 or more years. By definition, this is permafrost. And looking at this circumpolar, actually circumarctic permafrost map, which was prepared and published by International Permafrost Association, we can definitely see that permafrost is product of cold climate. So it's most of the masses of permafrost, they're surrounding the pole in high latitudes. There is some permafrost in low latitudes, but it's related to high elevations. So in general, permafrost changes from south to north, from discontinuous sporadic permafrost to continuous cold, thick permafrost. And definitely it's related, it's definitely connected to changes in climate. And there is one more interesting feature, that there is some permafrost under sea also within the wide shelves in the Arctic seas. There is some permafrost under the bottom of the sea. And because of permafrost is product of climate, any changes in climate will, of course, affect permafrost as well. And in terms of changes in temperature, permafrost reacts very rapidly to changes in climate. It doesn't take too long, just maybe several years, and permafrost reacts to changes in climate. But to change permafrost thickness or distribution, it takes much, much longer. So that's why to really understand or try to understand present-day permafrost state or distribution thickness, we have to go a little bit farther back and look at the at least one glacial, interglacial cycle to understand what, how this present-day permafrost was built. And also, it will be very helpful to think about it, looking in the past, to predict or try to project changes in permafrost in the future. So that's why in this presentation, I will start with this kind of going a little bit back and discuss changes of permafrost during the last glaciation and interglacial period. and related to these changes in permafrost, changes in environment. Then I will give some information on present state of permafrost, and then shortly discuss some possibility in changes in permafrost because of changing climate and some consequences of these changes. So it's a kind of a very simplified diagram of changes in last several 100,000 years, showing that climate was changing more or less cyclically. It was a period of each cycle about 100,000 years, and we are interested in, mostly right now in this last cycle, which started about 100,000 years ago, with very significant decrease in temperature globally, and eventually the so-called glacial maximum, last glacial maximum, was reached by about 20 to 25,000 years ago, and then it was significant change in climate, and it was rapid increase towards the Holocene, towards the last 10,000 years, which kind of very schematically shown on the second diagram. This Holocene time, generally much warmer than previous glacial period, so-called interglacial, also was, there were some changes in climate, but generally it was some kind of optimum of Holocene about 6 to 8,000 years ago. And since then, climate generally cooling, and the culmination of this cooling probably happened during the Little Ice Age about 200, 400, 600 years ago. So that's what climate was doing. Permafrost, like I said, followed these changes, and let's look what permafrost was doing during this period of time. So just for example, I will use some situation within the former Soviet Union territory, because we have the most available data for paleo-permafrost reconstructions from this area. That's why I'm using it as an example. But what it shows that during the, or around last glacial maximum, permafrost was distributed very widely in an area which was not occupied by glaciers or ice sheet. And if you look at this map, very significant portion of Europe was underlined by permafrost. In Russia, permafrost, southern boundary of permafrost was moved down to almost to Black Sea, Caspian Sea, and in Asia, permafrost southern boundary was way down south, covering almost all Mongolia and some portion of China. So that's situation with permafrost at this point. Also, I want to point that during that period of time, the stand of global sea level was about 120 meters lower than it is right now, and a very wide portion of the Arctic shelves was exposed to the very harsh climate environment, and permafrost was actively growing there during this period of time. So by this time, very thick and cold permafrost was formed in all this area. So also very important to note that the ecology of this area of permafrost was very, very different from anything what we see right now. So it was so-called mammoth steppe, or environment which this is kind of reconstruction with real lions and tigers. And it was just 20, 30,000 years ago in all this vast area. The most important for us, of course, that all these big mammoth grazers were able to survive there because of productivity of this grassland or very arid grassland was very significant, and lots of carbon was actually produced and sequestered in permafrost because of the, you see this treeless area was affected by winds and wind-blown sediments. The rate of sedimentation was significant, and in many cases, the dead roots and even stems and sometimes even leaves were buried in these sediments and frozen almost immediately after deposition. And since then, never had chance in the northern regions to be decomposed. So that's very important for us for our further discussion. So the major two features of this so-called ice complex, which covered this huge area, and some places in Siberia, the thickness of the layer was about 40 to 60 meters, and other areas it was less, but nevertheless very significant. So the two features very important for us. It's very icy permafrost, and also in a very rich organic soil in between the ice wedges. So these 2 points will be very important for our further discussion. So there is another photograph of this ice complex from northern Arctic Siberia. Also important to notice that there is some methane and carbon dioxide sequestered in both in the ice and in sediments around the ice. And in case of thawing of this material, these gases will be released immediately into the atmosphere. So very ice rich, very carbon rich, and also contains some methane and carbon dioxide. So after this minimum and around 20,000 years ago, climate changed very significantly, dramatically. It was a very significant increase starting somewhere 16 to 15,000 years ago, and it was continued into the Holocene. And of course, permafrost reacted, not immediately, with some delay maybe, but on this time scale, permafrost follow the climate very, very closely. So what happened to permafrost by the so-called Holocene optimum, sometimes 5,000 to 9,000 years ago, permafrost practically completely disappeared from Europe, and in Asia, in West Siberia, permafrost was actively degrading here, and surface of permafrost was lower than ground surface by several tens of meters. So the same is in this area, in central Siberia, and only in the northern part of East Siberia, permafrost still survived this Holocene optimum and still intact. At the same time, very significant changes happened within the Arctic shelves because of increase of the sea level. All this shelf area by 5,000 years ago was practically all of these areas were covered with ocean again, and the change in temperature was about 20 degrees Celsius, from about -20 to about -1.8 or 1.6. So that's significant changes in temperature on top, and also some reaction or interaction between saline water and permafrost, of course, immediately started permafrost degradation within these inundated Arctic shelves. So in the area where permafrost still stable, still cold, were also very dramatic changes. And this is two examples from one from Lena River Delta around it, and one from around Barrow from northern Alaska, showing that during that period of time, it was about 10,000 years ago, it was explosion of development of thermokarst lakes. So thermokarst lakes were very rapidly developing. Permafrost was thawing under these lakes and around the shores of the lakes. So even in cold, permafrost still stable in terms of climate. There's a significant portion of this permafrost was destroyed by thermokarst and thermokarst processes. Earthquake? So this is a kind of simplified cartoon starting from, it's not me. Starting from about 15,000 years ago, where the area surface was pretty flat with some ice wedge polygons actively growing. Then into thermokarst affected area about 12,000 years ago. And then in the area close to the shore with increase in sea level, this thermokarst depressions start to connect to ocean, forming some lagoons. And eventually, by the present time, permafrost is degrading under the sea bottom and also on the shore of the ocean. So all these processes release a significant amount of carbon which was sequestered for a long period of time in this frozen state. And I believe that at least partially because of this release in carbon, we can explain these dramatic changes in concentration of methane and CO2 during this transition period from the last glacial to interglacial time. So I would not say that most of this we can explain by this release, but actually we don't know. Nobody really made this estimation yet. But the degradation of permafrost played a very significant role in this increase in greenhouse gases during that period of time. So after Holocene optimum, it was cooling again. So last 5,000–6,000 years, it was late Holocene cooling, which eventually culminated in this little ice age, where temperatures were probably the coldest during all this late Holocene time. And permafrost, of course, reacted to this, establishing new, younger permafrost in the southern boundary of the old ancient permafrost. So this permafrost formed in the northern, very northern belt along the shore in the European part of Russia, and then in the more extent in Siberia. This permafrost is about 3,000 years old and about maybe 50 to 100 meters thick. And in the late, during the Little Ice Age, new, very young permafrost formed again along the southern boundary and also within the discontinuous permafrost zone as well. So kind of increasing continuity of permafrost in the discontinuous permafrost zone. And this young, very young permafrost, just 200, 300 years old, usually not thicker than 10 to 20 meters in thickness. So at this point, something happened again to climate, and we start to recover probably from the Little Ice Age. And this recovery was could explain some part of this recent warming during the last 200 years, but especially significant warming happened in the last 50 years of the last century. And you can see that it's a famous diagram, and we see similar similar diagrams today already. But what I would try to stress that actually the maximum increase in temperature is related to permafrost areas again. So we have significant changes in the environment, and as a result of these changes, of course, we have to expect changes in permafrost. So to know what permafrost is doing, we need a system of permafrost observatories, and I will show just two examples of it. One of them from Alaska, which very comprehensive system of permafrost observatories exists and developed by USGS. It's green colored squares, and by Geophysical Institute, University of Alaska Fairbanks. USGS deeper boreholes were measured periodically since 50s and 60s, and this system of boreholes, Alaskan transect of permafrost observatories, were established by Professor Tom Osterkamp from the Geophysical Institute, sometimes in the late 70s and early 80s. And we have continuous record of permafrost temperature with relatively shallow 60 to 80 meters boreholes, but without any interruption. And the very intensive system of permafrost observatories were at some point in the past was developed in Russia as well. Unfortunately, most of these observatories now not in function, and there's only few groups who continue to measure temperatures in some very limited number of boreholes. But and this is our big challenge to really to create this picture of circumpolar changes in permafrost. We have to reactivate measurements and compare with old measurements and produce this benchmark for future generations to look at the permafrost, how permafrost will be changing in the future. Just a couple examples, maybe from this permafrost observatories. One of them it's both of them from continuous permafrost, relatively cold, though you wouldn't call this cold permafrost, but it's a continuous permafrost zone, one in North Slope of Alaska and another in a very northeast part of the European north of Russia. And records about the same length, starting somewhere in the late 70s. And what we see here, actually very, very similar picture. So it was relatively warmer during the early 80s, and then cooling, some relative cooling in the mid 80s. And since then was significant warming. At some sites, about 2 degrees warming Celsius at 20 meters depth. It means that at the surface it was at least 3 degrees Celsius warming. And very similar situation here in Russia, where it's also about 2 degrees warming for the Vorkuta site, which is green. And also, I would like to note here that some sites, even in continuous permafrost zone, start to experience already very significant instability in permafrost and maybe even some partial thawing from the top down. This is data from our Canadian colleagues, Sharon Smith. It's from Western Canada, discontinuous permafrost zone. Temperature is much warmer, you can see, and also picture pretty similar with significant increase in 90s, kind of leveling during the 2000s. But temperature is really, really warm in many sites where permafrost is already very close to start to degrade, and that's a very important threshold. After that, many changes will happen to the environment. So now, during this period of time, well, all this what I showed before, it was increase in temperature, and it's not surprising because climate warmed, permafrost reacts and works. Now, the question is how much permafrost is thawing already right now? And we have examples where permafrost is thawing without any disturbances, so in natural conditions. And one of these very nice example, this work by Thor Jorgensen and photo by Thor Jorgensen, it's Tanana Flats north from Fairbanks in interior Alaska, where we see in many places in this area, permafrost is thawing and birch forest is dying. However, if you look at the data what Thor Jorgensen produced by looking at the very kind of very good analysis of sedimentation, and also from our modeling of permafrost dynamics, we can tell that this permafrost, which is thawing right now, is the youngest one, that one which formed during the Little Ice Age. This is the time last 1,000 years here on the scale. And permafrost existed only during the Little Ice Age. Some places maybe it started at some beginning, and now it's thawing from the top down. So what we see now, and the same situation in many other places where permafrost degradation was, or thawing, long-term thawing, was reported. For example, in Quebec and Manitoba, whereas peatlands is thawing right now, but it seems like these peatlands were formed and permafrost was formed during the Little Ice Age, not older. Well, the question is, what is the fate of permafrost? So that was stated before. Now we're going to fate. Well, if climate will not change anymore, it will stay the same. It is right now. Probably there will be some limited thawing of permafrost, and mostly it will be that one, the youngest one. And probably this older 2,000-3,000 years old permafrost will be stable, though very close to thawing point. The same as continuous permafrost. Of course, permafrost in shells will continue to thaw no matter what, because it's still much warmer conditions than it should be. So it's actually relic permafrost. But the major body of permafrost probably will be pretty stable if climate will not change. So unfortunately for permafrost, it's not the case. And we see many illustrations here in the previous presentations that expected changes in in climate will be very, very significant, and maybe more significant and definitely more rapid than anything in the last history which I just covered. So we have possibility that this permafrost will start to older permafrost will start to degrade as well. And in this case, actually, it's very important to know what is the age of permafrost, because generally it will be like rewinding the movie. So you start with the youngest permafrost thawing, and then older one will start to go, and then finally the oldest ancient permafrost will start to thaw. So we actually have some idea what will be the sequence of degradation, if it will happen, of course, if warming will continue. So we choose several sites where we should pay special attention for changes in permafrost for many reasons. Because first of all, it is exactly that permafrost what I described, very icy on one side and very very carbon rich on another side, and carbon is in form of very digestible for microorganisms as soon as this permafrost will start to thaw. At the same time, the temperatures in these areas in permafrost also is very close to zero. Some of them, even at some specific conditions, temperature already crossed this 0 point threshold. So all of these areas is extremely close to start this permafrost thawing, long-term thawing. Just simple modeling analysis using some moderate model for prediction for or projection in climate for the next our current century will give us some idea what we could expect if this projection will become true. So by the 2050, significant portion of this intermediate age permafrost will be thawing, and it will be thawing also in the whole belt around the continuous permafrost zone. So most of the discontinuous permafrost will be, well, some of them will be thawing, and by the 2100, we will expect a thawing of permafrost within all discontinuous permafrost. So all this intermediate permafrost will be definitely actively thawing according to this scenario, of course, and maybe some old ancient permafrost will be involved in thawing as well. So what will be the consequences? So actually we see some of them already. So it will be slope instability and landslides, and nice pictures from Banks Island. Also, again, with thawing of permafrost in conditions like lowland conditions, soil moisture probably will be increased significantly in this area, and maybe it will be too much water to hold forest, and boreal forest will turn into swamps and wetlands. On another side, with better drainage conditions, with thawing of permafrost will remove this barrier for water, and it could be actually turned into much drier conditions, especially in the sandy soils. And we can expect a replacement of boreal forest with steppe-like ecosystems. Permafrost degradation will, again, this new wave of warming and new wave of permafrost degradation will activate the thermocars, and not only in the southern regions, but also in a colder permafrost as well. And these thermocars will produce methane, and it was several publications already done on this topic of role of thermocars lakes and production of methane. Coastal process will be intensified not only because of warming, but also because of free of ice ocean will have much more mechanical energy to destroy this very icy cliffs. And again, the same ice complex will be undergoing this very significant destruction, degradation, and again, significant portion of this carbon will be released to the atmosphere or into the ocean with some other interesting consequences. Gas hydrates, it's much more speculative assumption, but it's also possible that with this warming and continuous degradation of permafrost in the coastal area can actually start to decompose gas hydrates, and it's possible again with this structure of permafrost already not really continuous. This gaseous methane from degrading gas hydrates could be actually delivered at least to the bottom of the sea and maybe into the atmosphere. There is probably some examples of this already. We can see this work by Igor from International Arctic Research Center. They did several cruises in the area of Laptev and the East Siberian seas, and they see both at the surface and at the bottom waters very significant concentration of methane, dissolved methane in the water, much higher concentration than it's supposed to be. Now, the question. Well, all this new production of greenhouse gases can increase CO2 both and methane concentration in the atmosphere, and can lead to new wave of warming and new wave of permafrost degradation. So it could be possible that it will be triggered, this positive feedback mechanism will be triggered, and we can see further intensification of this warming and permafrost degradation as well. And there's some consequences for, well, infrastructure in this case. So it's very typical every spring. I'm looking for this kind of sinkholes around Fairbanks, and almost every spring I can find very nice cases like this, and I photograph them, and I have many, many pictures of this kind. This is very icy permafrost degrading now along the big ice wedges, and forests, of course, destroyed completely over this permafrost. Infrastructure have pretty serious challenge with thawing permafrost, both buildings and pipelines and some other linear structures. Houses, this is also very probably famous already example, which was published in many reports. It's in Fairbanks as well. And finally, there's a very good Russian proverb, probably the same will be in English as well. So little kids, little problems, bigger kids, bigger problems. So thank you very much, and if you have questions, I'm very thankful. Okay.
You mentioned the methane being produced from the thermokarst wetlands. What about nitrous oxide? Has anybody looked at that?
Okay, so I'm not aware of this work. It's probably the nutrients in general will be released as well with thawing permafrost, and but I don't know any good examples to tell you about this kind of work. But yeah, it's a very interesting question. Yeah. Our question was if nitrous oxide will be released as well together with methane. Yes?
How well are the methane clathrate resources known as a function of in a warming scenario, and the release rate predictable?
Well, well, it's very huge uncertainty there, just from the point of view of pools, because estimates of clathrates amount in the world vary by 2 orders of magnitude. But even the smallest estimates, they're huge. I mean, even the smallest ones show that it's possibly, or probably, very probably, that amount of hydrates is larger than any kind of fossil fuel, other type of fossil fuels. So the amount is great. So now the question about how rapidly they can be released, also question on, not simple question. Of course, we have to distinguish between hydrates in the deep seas, in low latitudes, which is also in deeper than 500 meters. There's also a significant amount of hydrates there as well. I'm talking about northern hydrates under the permafrost and also under shelves. So under permafrost, probably there is no worry at this point about gas hydrates and under permafrost, on land permafrost. But under shelves, because of this history of 10 and more thousand years of degradation of this permafrost, there could be already some pathways already established, and the degrading hydrates can be delivered to the surface pretty quickly. The question about how we can estimate it, it's one of those questions, well, we don't know even. Even we don't think we know. Yes.
Your illustration of permafrost in Alaska, there's a band of it across the north slope, but there's also a lot going down the Yukon-Kuskokwim Delta area. Is that because of the type of soil, or is that because those are river valleys?
Thank you. Very good question. It's a question about on the map of permafrost Alaska, the continuous permafrost not only on the north slope but also in the Yukon-Kuskokwim Delta. So that's area one of those we think we know but we don't know. There's not too much data at all from this area. However, the data show that permafrost is very warm there, very close to 0 degrees Celsius, but at the same time it's almost continuous with very thick permafrost, some depth more than 100 meters. Explanation is this is actually a tundra area also. Tundra, it's not forested practically. So, and also maritime type of climate, which cold summers and relatively warm winters. In this case, with snow doesn't produce too much protection from cold. I mean, it doesn't increase temperature. And in this case, temperature at the permafrost surface will be, at the ground surface will be pretty much the same as air temperature. And mean annual temperature there is still below 0 degrees Celsius. So that's kind of explanation of it. But definitely this area underrepresented in our, if you look at this network of observatories, it's practically none there.
You mentioned some of the effects on infrastructure that flying permafrost can have. Is anyone looking at northern mines and tailings?
Northern
Mining.
mines and tailing. Well, it's a very serious question for Canada, I know, and I think there was almost annual meetings on this topic, and one of them I think coming pretty soon. So originally it was thought that permafrost is perfect barrier and nothing could happen to that. Now it's a very different opinion, and scientists and engineers pay very significant attention to this possibility. Especially, usually permafrost is not, it's saline permafrost actually because of this. It's not just pure ice, it's actually saline poor liquids there. In this case, degradation of permafrost could start much sooner than 0 degrees Celsius. So that's a very serious problem, yes.
Thank you.
Thank you. Okay.
That's excellent. Thank you. Okay. All right. Well, we've touched on many topics today, and still there are many more to go. We've seen that issues of climate change, how they affect the atmosphere, marine ecosystems, terrestrial ecosystems, the land, and permafrost. And now we're going to hear about people. Igor Krupnik is our next speaker. Igor is a cultural anthropologist and curator of the Northern and Polar Ethnology at the Smithsonian Institution of Natural History in Washington, D.C. Over the past 30 years, Igor has been involved in numerous projects studying the impact of climate change, preservation of cultural heritage, ecological knowledge of the Arctic indigenous people, particularly in Alaska, the Bering Sea region, and along the Russian Arctic coast. He's currently the coordinator of an international study of local knowledge and the use of local knowledge of sea ice by Arctic residents named SIKU, S-I-K-U, Sea Ice Knowledge and Use in the North. It's an IPY project. Dr. Krupnik has published several books, catalogs, and collections, including 2 edited volumes on indigenous observations of Arctic environmental change. The Earth is faster now in 2002, and watching ice and weather our way in 2004. And I just note that almost everywhere you go now, you see one or the other of those cited. He was the curator for the exhibit The Arctic, A Friend Acting Strangely at the Smithsonian. He's a member of the Joint Committee for the International Polar Year, and he was absolutely instrumental in bringing together socio-cultural issues, ecological knowledge, and environmental observation of northern indigenous people to the agenda of the International Polar Year. It's my pleasure to introduce Igor Krupnik.
Thank you, Mary. What's the technology here?
Or you can use that one, whichever you prefer.
Okay. How you click here? Just
Just this.
okay. Mhm.
And he's not, he has to change it up there.
Sorry.
So the guy in the booth. All right.
Okay. Thank you very much, Mary. I've been asked by the organizers to speak about Arctic people and climate change. And of course, Arctic residents are no strangers to this ongoing debate about global warming. They speak about changes in the environment passionately and with great knowledge. They're usually terrific public speakers on the issues of climate change. So I wish there was an Arctic resident speaking about this. So since I'm neither an indigenous Arctic person nor a climate scholar, I decided to add two more words to my paper's title. One is IPY and another one is science. Usually my job of a social scientist is to listen to what local people say about climate change and to make sense of these stories. Many colleagues see these stories by Arctic residents more or less like anecdotal evidence. So the task of this presentation is to explore and to illustrate to you how we may convert anecdotal evidence into science data for IPY. Studying Arctic people's knowledge and observation of climate change is a very young field. You know, I was listening to the previous presentation and people have data and records going from the 1940s and early 1900s and 1970s and 80s. We don't have this. Of course, Arctic residents have been observing and reflecting upon changes in their environment since the time immemorial, and they were very early kind of raising their concerns about climate change. It's just us scientists, Johnny, coming not late, but very late. So the field exists probably since the mid-1990s, just 10 years. That's very young. We don't have, I will spare you all these fancy charts or circumpolar maps. We don't have this. Not yet, maybe for the next meeting, but so far we don't have them. So when we started paying attention to what Arctic people say about climate change, the field actually literally exploded. We have produced numerous papers, a few published volumes as you have seen here. We have done some interactive CD-ROMs, very nicely done. We have video documentaries on indigenous people observation of climate change. We have a few exhibits, including one that was mentioned, A Friend Acting Strangely, which was on display in Washington, D.C., is now traveling in Canada. There is another exhibit right here on campus, and we all have these nice catalogs in our bags, so I wish we all kind of go and look at this exhibit. On top, Arctic residents' perspectives on climate change have been featured very prominently in the most recent Arctic Climate Impact Assessment, ACA. So it's hard to think these days of any major study of Arctic environmental change that does not incorporate, or at least does not make a reference to the knowledge and observations of Arctic people. So the just started IPY 2007-2008 is both a good illustration to and a strong driver of this new trend. All previous IPYs, including the IGY of 1957, have been primarily, if not exclusively, geophysical initiatives. The main focus was in meteorology, atmospheric and geomagnetic studies, later in glaciology, geology, and ocean sciences. We have hardly any record of polar residents' involvement in earlier IPYs other than them serving as guides, dog drivers, unskilled laborers, low-level assistants. So that was, for decades, the image of polar science was like that. So a tough, bearded white man standing on polar ice sheets or on the decks of icebreakers with some interesting instruments. So the new IPY cannot be more different with a smiling face of Inuit kid, although it has some bearded white man over there, but still it's a very different one. This transition has eventually transformed the face of polar science, long seen as exclusively male and primarily geophysical domain. Robin, I'm doing it especially for you. So you see Admiral Byrd and his team in Antarctica in 1956. So that's the way polar science used to be done some 50 years ago. Also, the new IPY is taking place in a totally different social environment. Researchers in the polar regions now interact with a very new generation of educated and technological astute local residents. See those people, they operate the far more fancy machinery than we normally use here. And many Arctic areas now feature modern schools, internet connections, and youth very interested in science and technology. So it comes as no surprise that many groups representing polar residents and Arctic indigenous people responded to the new IPY call with great enthusiasm. All major northern organizations, from the Arctic Council to the Inuit Circumpolar Conference, Aleut International Association, Russian Association of Indigenous People, the Sami Parliament, I can list more and more, are actively involved in this IPY as participants, supporters, or initiators of its science and outreach projects. Their enthusiasm has been fully displayed at a new event which was called the Indigenous Opening of IPY, which took place in the Sami town of Kautokeino in northern Norway exactly a month ago. Many Arctic residents see IPY as the first major science venture in the history of polar science to which they have been invited and in which their knowledge of polar environment has been actively promoted. So the now famous honeycomb chart gives us some good metrics to measure Arctic people's participation in IPY, and I thank David Carlson for providing this. And here I'm switching from talking about scientists at the universities and research centers in places like Fairbanks, Tromsø, Reykjavik, or Murmansk to the places like Kautokeino, Nuuk, Iqaluit, or Barrow. Of the 220-some endorsed IPY projects, over 60 are focused upon Arctic residents and northern communities. So almost a quarter of IPY endorsed initiatives. On top, the so-called human dimension is added to many interdisciplinary initiatives as well as to some 30 projects in education outreach. So Greta Holsrud and I made this kind of organization of these projects by various fields of science disciplines and ranked them by the overall number of the projects in each category. And we also identified projects with strong participation of Arctic residents, shown here in parentheses in the last column of the table. So it, again, no surprise, the study of indigenous knowledge and of the documentation of polar residents' observation of climate change made by far the largest field. It also has the highest participation of northern people. None of the previous IPYs would have ever considered the documentation of indigenous knowledge to be a topic for polar research. So please be aware of that. Now, how we may convert local knowledge into IPY science. So if participation in IPY is to bring some tangible benefits to both Arctic residents and polar researchers, each party has to grasp how other knowledge system operates. And they indeed operate very differently. That implies certain steps to make the two systems compatible or at least open to interaction. I believe it is the lack of such understanding that is responsible for a popular view of indigenous observations as merely anecdotal evidence compared to the solid data of modern science. Of course, local knowledge, very much like science, is dependent upon careful observation or data collection. However, the pursuit of local knowledge requires several levels beyond data collection, and most of my colleagues in the field of indigenous knowledge studies would certainly agree that indigenous experts follow many of the same analytical steps as do modern scientists, though in their own specific ways. Much like scientists, local experts normally exchange and cross-check their individual records, and they convert them into a shared body of observations that is usually open to criticism, at least among them. They analyze the signals of change, they pose questions, they formulate explanations of the phenomena they observed. When the studies of Arctic indigenous records of environmental change took off less than a decade ago, we were at the beginning literally overwhelmed with the sheer wealth of local knowledge and local observations, literally. We were eager to fill articles and books with the quotations from Arctic elders, just nothing, just get them under the cover and let them know. And true, an articulate and watchful Arctic person can present an amazingly comprehensive account of change in his or her native area. And I personally had a few of such examples. You know, you turn on your tape recorder, and for 30 minutes, a person just talks about what's happening to his or her place, and you get everything from birds to ice to grasses to shores to oceans, not ozone depletion, but many other things that person observed. So much of our early use of indigenous observations of climate change has been just limited to this careful listing of various individual quotations, particularly in some of the public materials. So that was the level we were originally at. Soon, however, scientists began to apply some analytical tools to organize indigenous records, such as comparative studies or matrix tables. Very helpful, original way to structure the wealth of data, arranged by geographic area or ecosystem components. Both tools prove that Arctic residents observe a consistent pattern of change across the polar regions, and that they interpret this change in a comprehensive way. You can see this illustrated in one of the earliest publications on indigenous knowledge. At this observational level, indigenous expertise is now firmly considered invaluable, even essential to polar research, and we are to thank ACA for making it sure and real for everybody. The next step, still in its infancy, is to focus upon cases and records where local and scientific observations disagree or offer different, often very distinctive interpretations. And there are some cases where we do disagree. The goal here is to grasp specific features of scientific versus local systems of knowledge, such as different levels of scaling, non-matching indicators, and much more, and many more. Again, I have to admit that our understanding of where native experts disagree with scientists about the polar processes and why so remains rudimental at best, and we'll probably have to stop, picking things where we agree and using citations from native observations just to support our scientific kind of conclusions and predictions, and look into places and cases where we do disagree. I will use the remaining 15 minutes of my talk to illustrate how Arctic residents' records of climate change could become a valuable addition to IPY science program. It can be achieved through a certain mutual adjustment of observational protocols. That, to me, is critical. On the one hand, scientists have to accept that records generated by local observers are indeed special, despite often remarkable differences in data collection and data management processes. On the other hand, local monitoring of climate change may be arranged so that it follows certain basic criteria in science data collection, such as transparency, long-term series, and independent verification. That's where we shift from anecdotal evidence to science data. Indeed, indigenous research process, including data collection, has its own protocols that are very different from those used in academic science. Firstly, indigenous records are rarely kept in writing and rarely kept in published papers so that they may become accessible to everyone. Secondly, more often than not, they are hard to be tested by common statistical procedures like time series, mean scores, standard deviations, etc. So they are so far cannot be subjected to the standard procedures used by scientists. Thirdly, they often hold to their specific terms of references, such as community-based memory or statements by elders, rather than instrumental databases of science publications. Nevertheless, the sheer volume of indigenous participation and data to be generated through IPY projects may help build a new momentum. It has already stimulated efforts to develop more standardized procedures for local observations and management of indigenous records. So the last section of my talk will use this IPY project that Mary mentioned, which is called SIKU, in which I'm involved to illustrate what can we learn from our local partners and how it may advance the IPY science. SIKU is an international initiative to document indigenous observations of sea ice and changes in sea ice use among indigenous residents of the Arctic. Incidentally, our project title has a meaning. This is the most common word, siku, used by the Eskimo Inuit people all across the Arctic, from Chukotka to Alaska to Canada to Greenland. Under the Alaska-Chukotkan portion of siku, about a dozen indigenous observers will conduct or are already conducting daily observations of sea ice and weather conditions in their communities. This story is about one of them. Leonard Apangaluk Sr., a hunter and a community leader from the Yupik village of Gamble on St. Lawrence Island, Alaska, from this place. He is a proud participant of IPY. He also continues a long tradition of his family's collaboration with Smithsonian scientists that goes over 3 generations. Oops, sorry. Over 3 generations. That's a Pangaluk uncle who used to work with every scientist that appeared at Gamble between 1912 and the time he died in 1946. Apangaluk supplies on a systematic basis daily records of sea ice, weather conditions, wildlife, and local subsistence activities. He will continue his observations hopefully through the second IPY winter of 07-08. St. Lawrence Island hunters' knowledge of sea ice has been extensively documented in recent years, including a bilingual book, now I can probably go back then, that Henry Huntington and I published in 2004 in collaboration with 2 island communities. Island residents have a keen understanding of significant changes in their environment, and they speak loud and clear about the transitions they observe and the concerns they have regarding their economy, culture, and way of living. Apangaluk's systematic observations help convert those individual statements into scientific records, as can be seen from the following few illustrations. New pattern of fall ice formation. The islanders have a very detailed picture of how the new sea ice is formed around their island, or rather how it used to be formed in the old days. Usually it started with small chunks of floating iceberg they called kulusit, which appeared from the north in late September or October. Most would melt or would be washed ashore. A few would merge with the locally formed slush ice, usually in November, to form the first locally formed ice. At this time, which means mid-November, there'll be a rapid shift in the direction of the prevailing winds from primarily southerly to primarily northerly, followed by a drastic drop in daily temperatures. By late November, the main ice pack, multi-year ice called Sikupik, would arrive from the north, often smashing violently the fields of locally built ice. I'm just retelling what people, keep telling me through these years. So crushing, breaking, refreezing of the various types of ice would continue through the month of December until a more solid winter ice is formed to last till spring breakup. Since the 1980s, hunters started to observe changes to this pattern, so much earlier than we scientists started to notice them. First, floating icebergs, kulusit, were late to arrive, often by a month. Since the late 1990s, they stopped coming altogether. There are no more floating icebergs coming in the fall. The new ice started to form entirely out of frozen local slush ice, And then the main multi-year pack ice ceased to arrive until January or even February, and in the last few years it didn't come at all. When the ice finally comes from the north, it's not a solid multi-year ice anymore, but rather a thin, young, dirty, black ice that was formed further northward. And hunters can tell you even when and where this ice has been formed. And they say, this is not the real ice we used to have for the winter, sea Krupnik. Because of this new sea ice dynamics, the arrival of winter conditions on St. Lawrence Island is now being delayed by at least a month, if not more. A Pungaluk observation through November-December 06, this first IPY winter, helped document this new pattern with great detail. What's unique is that his daily records may now be compared to the logbooks of early teachers from his village of Gamble that covered 3 subsequent winters, 1898, 1899, and 1900s. According to Pungaluk records, no floating icebergs were seen in 2006. The change of wind regime from southerly to predominantly northerly took place on December 5th, 2 to 6 weeks later than in the period of 1898-1901. The temperature dropped solidly below freezing again 2 to 6 weeks later than a century ago. The first slush ice appeared December 10th, 2 weeks later than in the early records of teachers. And locally built slush ice solidified and expanded rapidly. On December 16th, a Pungaluk recorded that, and I quote, when this locally formed ice gets thick and it encompasses the entire Bering Sea around our island, our elders used to say that we have a winter that is locally formed. Very eloquent way to describe this. His logs also substantiate claims of other hunters that point to the change in sea ice and weather regime in wintertime as well. With the lack of solid multi-year ice pack, people have to adapt to a far less stable local ice that can be broken by wind, storms, even currents at any moment. According to the elders, this ice is no good, and it's too dangerous for walking and winter hunting on foot, like it used to be in the old days, or with skin boats being dragged over the ice. Instead, hunters have to do this. Rely upon a far more dangerous hunting for seals and walruses in dense floating ice that is now a typical activity in wintertime. During the early teachers' years, this type of hunting has been started normally in late March or early April. Winter conditions in Gamble with prevailing northerly winds often intercede with few days of violent storms and warm spells brought by southerly winds. It happened twice in winter of 1899 and 1900 and 3 times in 1898. Another elder from Gamble claims that those warm spells have been typical in his early time, and that the difference is that now these waves are just much longer, they last for several days, and that is indeed, that can be seen from daily records created by Pungaluk. So the warm spells often lead to the numerous episodes of ice breakups and new ice formation every winter. In the middle of the winter, the ice is broken, driven off, formed again. At least 4 episodes of this kind of complete ice breakup and refreezing has been documented during this past winter. On January 10th, I have a record. It's unusual to have swells and to lose our ice in January compared to normal year in the past. This ice that covers like 90-10 of the area disappears with the temperature and strong swells. And then again, we get this long quote, which I just summarized. The climate change has accelerated over the past 5 years, where severity of winds and erratic temperatures occur more frequently every year. There's one more thing that elders keep noticing, that in the old days, despite snowstorms and warm spells, there were long periods of quiet and very cold weather with no winds. And those cold stretches were very good for hunters, for predicting of weather, for traveling. And in the teachers' records, those long stretches are very well identified. They lasted normally for 2-3 weeks each month, so it was a long period of quiet, cold weather. Not anymore. According to the logs of this past winter, there were just a few periods of relatively quiet weather. They lasted for a couple days only. During the month of December of '06, there was just one day when the wind was below 9 miles per hour. Everything else was 20 to 30 to 40 miles, while in December 1899, the first 10 days of December were quiet and calm, and then there was another week around Christmas when it was quiet and nice. So the earth is indeed faster now, as native people keep saying. One more thing, and I'll come to my conclusions. Wildlife and subsistence hunting. Indigenous records are so densely packed with references to subsistence hunting and wildlife. Bowhead whales. They used to pass by St. Lawrence Island normally in October, November, early December. They're now being hunted and seen off Gamble in the middle of the winter, in February. So they, in spring of 1899, the first bowhead whales were hunted on April 6. This past year, the first effort to hunt bowhead whales happened on February 6, so 2 months earlier. And Apangaluk reported seeing bowhead whales for all full week in February. Whales were also seen in Barrow, which means that bowhead whales are not moving, or at least some bowhead whales are not moving today down to the southern portion of the Bering Sea where they used to go in the previous years. There are many other references to other animals like beluga and Pacific walruses that I just have to skip because of the shortage of time. There are also references to the birds that cease to appear, and we have heard this from earlier presentations that this erratic behavior of wildlife populations, has been noted by scientists. Now we have the testimonies of indigenous people on what they see. Conclusions. Those few examples from the first months of systematic monitoring by local observers indicate a consistent pattern of ice and weather change in the northern Bering Sea. It includes not only a much shorter presence of sea ice, with later new ice formation in the fall, earlier breakups in spring, but a different ice regime. The leading role is now being played by young first-year ice. There is no multi-year ice anymore. Many types of ice are becoming rare or have disappeared. Now we can speak not only of endangered languages, we can speak of endangered ice. So like the floating iceberg, multi-year ice, multi-layered ice built of all the new ones, and many more. The ice is also very unstable, and both hunters and animals are trying to avoid this type of ice. Another clear message from hunters' observations is that the northern Bering Sea ecosystem shift, recently postulated by scientists, is for real. Arctic residents refer to such ecosystem shift in every record of climate change they produce, although they use their own indicators and their own flag species. They're extremely worried about the impact of such ecosystem shift upon the economy, culture, and lifestyles, and as Apangaluk put it, predictability of our game animals of the sea are inconsistent and erratic compared to how it used to be back in the normal seasons. We, the hunters, along with marine mammals we hunt, are truly at the mercy of our rapidly changing environment. My last point is that local observers should be an active part of any systematic Arctic observing network built for the IPY years and beyond. Many hunters used to work for small bush airlines. They're trained to keep daily log of weather conditions. They're familiar with the practices of instrumental observations, sea ice monitoring, and weather forecasting. Some northern towns like Gamble, Barrow, Nuuk, or Kautokeino have historical records of weather, ice, and snow conditions going back to the era of the first IPY. Several sites have still active or former weather stations whose readings can be used to match the records of indigenous observers. That would help introduce cross-checking, time series, and other data processing techniques of today's science. Arctic residents' multi-year and multi-generational observations are too precious a record to be ignored or dismissed. Besides, conditions in places like Gamble, with shortened ice season and the recent loss of multi-year ice, may offer valuable insight into the status of the ice-free Arctic of many climate models. They predict the loss of multi-year ice by the end of the century. And in this case, Arctic residents' practical and integrative vision of their environment can be invaluable to our understanding of impacts and linkages in this new Arctic system to come. There is one more thing that we learned from Arctic people's participation in IPY. At local meetings, people are always polite, and they're usually very respectful of each other's experience. They praise great knowledge, and they honor good oratories. Those values hopefully may be reinforced in the polar research community to make another legacy of Arctic people's contribution to IPY science. Thank you.
We can take a few questions.
Yeah, okay, I will.
There have been some parallels between events now and like the Dust Bowl era of the 23rd century. And then we went into a cooling system. Are there any indigenous records or historic knowledge about what happens on the other side of the tipping point? Because that would be something they know that we don't even know about.
They are. Actually, we can, in a way, kind of divide what native people say about climate change into very different types of testimonies. And one could be said, it happened before. We have seen this before. And another one is, the Earth is faster now. So if it happened before, so then we have a knowledge and explanations. If the Earth is faster now, we don't have knowledge. So just as in science, there are two contradicting schools of indigenous interpretations. So the answer is yes, and it is more than yes.
So have you actually come across that where you've seen where they've seen a warming trend, maybe not as severe as this, but physically what happens when it comes out of the warming trend?
Yes.
That would give scientists something to look for to see where that tipping point is.
I cannot agree more. The problem is that you have to model it to the level of the precision you need. You know, you have to recreate, you know, if this is a cooling, if this is a warming stage today, you have to create a mental process in which a person can tell you about what's happening when the cooling is coming with the very level of detailness you want us to have for the scientists to build a model. Am I talking this clear?
From an intuitive perspective.
Yes.
Like, do the clouds get thicker and then the cooling comes, or some general atmospheric condition that would give us insight into where to start looking if a tipping point changes?
Come and talk to people.
A comment perhaps, and more than a question. I like very much that we have all the people now in the north involved in the international polar year. It's a very different point, as you said. I also like your final point, namely respecting our elders and seeing how we can bring some of the culture from the local residents. What I have a problem with when you talk is that there's an intermix of words: local residents, Arctic residents, indigenous people. Now, in some places, indigenous people mean the people who've been living up in the high north and the only people living up in the high north. In other parts of the Arctic, indigenous people does not mean an exclusive group living in the... And so when you say we should bring local observers into something, I thought that completely. But there is a problem in the way you talk, maybe not deliberately, in that if you say it's indigenous people bringing in, well, what do we do then elsewhere? Like in Iceland, where there's for years people living look like Krista and myself. In northern Norway, where many thousands of people, yes, people are living both looking like Sami and looking like myself. So I think we have to sort out, because if we go the line you indicate, we could, and I don't think that's your indication, we could go the way, so there's going to be a split here. Certain people are better at looking at this than others. And I don't think a local observer is better think this is a European, North America difference, and to some extent European, Russian difference. Because in a certain market program like IPY, we need to be fairly clear what we are talking about.
May I have just a minute to respond? There's one big difference. I agree completely with what you're saying. One big difference is that non-indigenous people living in the north used to be literate for many, many generations and centuries. You have Icelandic sagas documenting climate change since 9th century or 10th century AD. So this knowledge has been successfully used, and in many Nordic countries there were efforts to bring local correspondence. Back in the 1800s, people contributed to the knowledge generated by local societies, museums, universities through this kind of correspondence network. Indigenous people are, in this regard, latecomers. So maybe the rhetoric is a little bit inflated because we are welcoming the new arrivals to the science pools because nobody questions the validity and the value of knowledge of literate people living in the north. So it's not a distinction between North America and Europe, it's a distinction between literate communities and those who gained the literacy very recently.
Thank you, Igor. That was great. And I want to welcome our new participants or our new attendees and invite you to come and have a seat if you're just coming in now. These are locals, people who live in Hanover and the area around the area. And we're delighted to have you here. For everyone just arriving, this is part of the Arctic Science Summit Week, a week long of discussion, planning, discussing science surrounding climate change and new international research activities in the Arctic. So welcome. Also going to welcome now our keynote speaker, who's Professor White. Jim White is a professor in the Department of Geological Sciences and Environmental Studies program at the University of Colorado. He's a fellow in the Institute of the Arctic and Alpine Research, and he's past director of environmental studies at University of Colorado. And Jim was instrumental in helping to establish and grow that program over the last decade. Jim has a wide area of research interest, but they all revolve around human impacts on the environment. Specific areas of his research including studying the global carbon cycle, both modern and in the past, and reconstructing past environmental conditions using ice cores. Jim was one of the first scientists to identify abrupt climate changes that are typical of large climate shifts on our planet. He's a highly cited author on the geosciences and one of the top 0.5% in his field of citations in his field of work. At the University of Colorado, he teaches a large lecture class in environmental studies, as well as a course on energy, carbon cycle, and climate change. He's actively engaged in exploring new paradigms of education in environmental studies. And he has been very active in working hard to break down the disciplinary barriers that exist between the social sciences, natural sciences, journalism, arts, and business in order to better train students in the area of environmental change. It's not surprising to see Jim talk about journalism and science or climate and business. I mean, you never know what he's going to talk about, which combination. But we're very pleased to have him as our keynote speaker, and he's going to talk about what you should know about Arctic climate change, why it matters. Thanks, Jim.
It's been an interesting afternoon for me because I had this talk I was going to give, and throughout the day, starting with Arden's talk and going through it the entire day, all of my slides got taken, all right? So while you guys were speaking, I was pitching out one slide after another because you didn't need to see that again, and so I came to this. So we got an hour, right? All right, no, I will repeat a lot of what people have said today. What I'll try to do is put a little bit of a different, not spin, but a little bit different look at it. and try to hopefully bring a lot of Arctic science into a broader context, and certainly into the context of decision making and communication to the public, etc. A couple of advertisements right up front. International Polar here. We've heard about this over and over again. This is very much a focus of what we're doing here. I just want to advertise the Polar Research Board here and the National Academies. This is their vision report. You can get it online. My spin for IPY, it's not just a year, folks. It's a responsibility. Now, I mean that seriously. We do science out of a number of motivations. Certainly, one motivation is curiosity. I want to find out what's going on. We also do science out of a sense of mission. We have a purpose. We get going, okay, I want to find out. Frequently, we band together with a bunch of colleagues to do mission-oriented research. I think over the last 10 or 15 years, those of us, particularly in Arctic science, Antarctic science, polar science in general, we've gone towards and reached a point of responsibility in our research. I think we have to do what we do. I think decision makers in the public absolutely need the information that we produce. And if we don't produce it, I think we're remiss. I think we have that R word, that responsibility word that my 12-year-old doesn't like and my 19-year-old absolutely hates. But we, as adults, quote unquote, I think need to accept that responsibility and treat the research that we do both with the respect that Igor told us to treat each other with at the end of his talk, but also with that sense of responsibility. All right. Have you heard a little bit about climate change lately? I believe you have. I'd like to show you the guy on the left here because he got to wear a tuxedo and get an Oscar using your data. So in all fairness, I would like to encourage all of you to go out, get yourself fitted for a tuxedo, because it's coming your way, right? All right? Yours is coming. The IPCC report came out recently, and I just went through it and I said, I'm just going to steal the figures out of here. We'll see how many of these figures have something to do with the Arctic, something to do with ice core, something to do with sea level, things like that, and indeed, they all do. So here's sea level. This is one of their first figures. CO2 levels are rising. And you see this wonderful little ice core data sitting here. It's not just CO2. We'll come back to this. All ice core data floating in here. We wouldn't really have a good idea about the baseline for greenhouse gas increase if it wasn't for the polar regions and the wonderful repository that we find on the ice sheets. This one we saw earlier today, and I think this one really illustrates just how important the Arctic and polar regions are in this IPCC report and in climate change in general. Global average temperature, we can't take a whole lot of credit for that. I mean, some credit, some fraction credit. Sea level rise these days is a temperature issue, but increasingly, as we've seen today and as I'll talk about, this is an ice sheet issue. And certainly the dangerous levels of sea level rise, and by danger, I mean money, come when the ice sheets begin to shed ice and sea level rise really begins to accelerate. Finally, northern hemisphere snow cover, all right, snow. There's a word that we can all relate to, all right? So if you look at this picture here, temperature's rising, it's not just temperature. A lot of that has to do with the Arctic region as well. So we're going to talk about here, I'll go quickly through a lot of the slides because you've seen them before, but again, I'll try to give you a little bit of a different look at it. We'll see how the Arctic feeds into this through snow and albedo, sea ice, sea level rise, abrupt climate change. We've heard about Arctic carbon stocks. 5 years ago, if you'd gone to a meeting, you wouldn't hear much about Arctic carbon stocks. Now, finally, there's been a whole bunch of people, Vlad and others, toiling in relative, I wouldn't say obscurity, but definitely not getting the publicity that they deserve, given the kind of important information they were collecting concerning the stability of these Arctic soils, this permafrost region, these lakes, etc. You've heard about all these today. Let's try to place them into a broader context. But first, I want to start with some basics. I don't get very many opportunities to stand up here and rant and rave. And so what I'd like to do is start with some basics about climate. We have some new friends here in the audience who are not scientists. And for those of you who are scientists, I want to give you a little bit of my view about global warming, about how to talk about this. All right? Seems like you can't have a beer with friends these days without somebody asking, is this global warming thing real? Right? I don't think I've been on a plane ride in the last 5 years where the person next to me inquiring what I do and what they do, they don't turn around and say, is this global warming thing real? So how do we answer that question? I answer the question through basic physics these days because I think everybody can grasp the next 3 slides that I'm going to show you. First, we know a few things about basic physics. Molecules only absorb the energy that fits them. That's basic chemistry right there, basic physics. The sun's energy passes through the atmosphere. It's absorbed by the Earth. And as it is re-radiated to the atmosphere, the Earth's energy, this is something that my undergraduates in the introductory environmental studies class miss all the time. It's the Earth's energy that gets trapped by greenhouse gases, absorbed in the atmosphere. And that energy is kept in the atmosphere for some extra period of time. That extra residence time of energy is the greenhouse gas effect that we talk about. Now, none of this is controversial. Absolutely none of this. We've known about this for a long period of time. In fact, greenhouse gases are an important part of the Earth's energy budget. We know from studies of the Earth from space that we have a temperature, a black body temperature we call it, of roughly negative 18 degrees C. That's about, what that means is that we're far enough away from the sun that we are basically supposed to be a frozen planet. If we were closer to the sun, we'd be a warmer planet. Farther away, we'd be a colder planet. But this is too cold, at least for advanced life. Maybe too cold for life. I kind of doubt that. But certainly, particularly given what we know about the bottom of the Antarctic ice sheet these days, but certainly too cold for advanced life. The Earth's temperature with greenhouse gases is about plus 15 degrees C, which, as we all know, is pretty darn cozy. So greenhouse gases raise the temperature of the Earth by roughly 60 degrees Fahrenheit. Natural, and we knew this 50 years ago, all right? We had this information. This is long before we got all excited about global warming. We knew that greenhouse gases were a natural part of the system. And so one of the actual funny questions I get when people come up to me is the greenhouse effect real? And kind of, yes, it is real. We've known about this for a long time. It's really not controversy at all. As a matter of fact, it probably makes the Earth habitable. Now, we know how greenhouse gases work. We know that greenhouse effect is real. We know it raises the temperature of the planet. And we know that greenhouse gases are increasing. All right? We know this from our wonderful ice core work. We have at the top here carbon dioxide. I've shown you this before. Cruises along, takes off. I'll show you this in a little bit more detail here in a while. This is from this is the beginning of the Holocene, roughly about 10,000 years ago. In the center one, we have methane. I can't read this. Methane. In the bottom one, nitrous oxide. These are the 3 natural greenhouse gases, at least the longer-lived greenhouse gases. Carbon dioxide levels are about 30% higher than they have been for 10 to 20 million years. All right. Methane is about 300% higher. We don't really know how that looks if you go way back in time, but we know at least 650, actually we know about 850,000 years ago what it looked like, and it's certainly higher than today than it has been any time in the past. And these chlorofluorocarbons and some other greenhouse gases are human-made, so they're new to the atmosphere. All of these things are going up. So greenhouse gases, we know the physics, we know they warm the planet, and we know they're increasing. With that that very simple piece of information, you can pretty much convince anybody, even the salesman I sat next to on the way here, who looked at me and said Al Gore was an idiot. I said, okay, let me talk to you about global warming. These 2 fundamental concepts, greenhouse gases warm the planet, greenhouse gases are increasing, make it very, very difficult to imagine a world with significantly more greenhouse gases that is not warmer. Right? Even my neighbors and friends have no trouble grasping these simple stuff. Now, this to me is one of the most important pieces of information that we've gotten from the polar regions. This happened to come from Antarctica, but we'll steal it for the moment here. This is on the bottom here, this is paleoclimatological time running from left to right. Many of you in the room are familiar with it. Others hate us for this. With temperature running back in time, you see interglacial periods bouncing along roughly over 100,000 years. We saw this earlier with glacial periods going up with glacial periods in between. You see the carbon dioxide levels. You take this data, you plot one on top of the other, and it becomes very difficult not to recognize that there's strong relationship between carbon dioxide levels and climate on this planet. We see that not only today. I was just at a meeting in Chicago, something called the Pittsburgh Conference, which is a bunch of analytical chemists. I mean, a bunch, like 25,000 analytical chemists, and they're a little less wild than we are. But we won't go into that. Anyway, they had a conference, one of their first sessions ever about climate change, and a few of us came and talked about the relationship between greenhouse gases and climate. I covered the last 100,000 years. Others covered 55 million years, and others covered 600 million years. Right? So we had pretty much the whole thing covered. Remarkably, this relationship between temperature and CO2, that scaling between how much CO2 you have and how much temperature you have, is that same scaling exists long, long into the past. So there's something fundamental. And I'm not arguing cause and effect here. Certainly CO2 is, as I said, is a greenhouse gas can warm the planet. But there's a fundamental relationship between the temperature of this planet and the amount of greenhouse gas, particularly carbon dioxide we have. That relationship right now is broken, as you can see. This is the current rise of CO2. The temperature is not there yet. We know that there's inertia in the system, and what this tells me with almost a very, very high degree of certainty, to use the IPCC language, it basically tells me this: temperatures are going to rise. And unless we actually remove CO2 from the atmosphere, temperatures are going to rise quite a bit. All right, so there's a lag in the system, warming's coming. We've got pretty much a broken system. But this relationship between CO2 and temperature, I have made the analogy that this is like two people handcuffed together. Occasionally one leads, occasionally the other leads, but unless you're going to cut an arm off, they're going to follow each other very closely. All right. The Earth is moving. Hopefully it was good for you, too. Greenhouse gas milestones. On this previous slide, I want to show you, I think this is something we've seen before, but it's a very important point to stress when you talk to people about greenhouse gas levels. During interglacial periods, greenhouse gas levels, 280 to 300 ppm. Nice little, I use 280, sort of an average. During glacial periods, roughly 180 parts per million. So actually, if you take a step back and you look at this, for those not familiar with looking at this data, note that there seems to be a lower level of CO2 that's not violated. There seems to be a lower level of temperature on this planet that's not violated over the last million years. There seems to be an upper level that's fairly well inviolate, fairly well, and an upper level CO2 that's fairly well inviolate. Why we have those thresholds, we're not 100% sure, but it is interesting that we have them, because if the pre-industrial level is about 280 and the full glacial level is about 180, that's about 100 parts per million. Nice round numbers. I use these nice round numbers. This is what the nature has been capable of doing over the last million years. And by the way, creating ice sheets that are covering where we are today in most of Canada and Fenno-Scandinavia, everything. So huge differences in climate associated with this 100 part per million change. We saw earlier today, I forgot who showed it. Was it you, Len? I don't remember. A number of 381. I'm conservative. When I do my global calculations, I try to be as conservative as possible, because I get a number around 378. And I think when we hit 380, it ought to be party time. Because at that point, human beings will have changed the mean carbon dioxide level on this planet by an amount that nature was capable of doing at a maximum over the last million years. That's impressive. I mean, that's just fundamentally impressive. And I think every now and then we should, as human beings, stop, take account of just how big and impressive we are on this planet. Now, you may not like the fact that we're impressive, but don't at least abandon the knowledge that we are impressive. All right. Just want to take a very quick point here. I wasn't going to show these next three slides, but I'll show them to you, and it'll probably get me clobbered, but we'll do it. This is another question, another point that I get in these airplane conversations, that the global climate system is way too complex. And indeed, we as scientists spend most of our time delving into those complexities. That's where the interesting stuff is. That's where the really, it's like eating a lobster. You get into the tiny little bits in there that, that's where the good stuff really lies. Occasionally, while you're eating a lobster, take a step back and note you're eating a bug, okay? That's what I'm going to talk about here. It's a myth that the global climate system is too complex to be predictable. If you look at this beast on a large scale, on the global scale, there are really only 3 big climate inputs into the system. You need to know something about how much energy we get on the planet. You need to know something about the reflectivity of the planet, including aerosols, snow, etc., the albedo of the planet. And you need to know something about greenhouse gas levels. With those 3 things, you can reproduce temperature quite well. And there's been a number of studies. This, again, was stolen from the IPCC. But there's a number of studies that have put these 3 things into models. And you can, if you want to take out the greenhouse gas, use natural forcing only. As you can see, the warming of the last 20 or 30 years, we cannot reproduce except when we put anthropogenic increases in greenhouse gases into the system. And this is the basis upon which I think it's very easy to say that human beings are causing climate change. Now, I would point out, and this is fun, do it. You can get the basic input records for solar incoming energy. You can get the basic greenhouse gas records, and you can get records of sulfate from ice cores or pretty good records, a number of other places. And you can throw those into an Excel spreadsheet, and you can do this yourself. You don't need a GCM to do this. You can do it in an, as a matter of fact, if you're really, if you're cranky enough and getting up there, you can do pencil and paper and actually, write it out. But I can do it on an Excel spreadsheet. I'm too bad with the pencil and paper to do it. The fact that you can do it that simply and that easily tells me that there's simplicity in the system, and that when you get hit with this notion of complex climate system, take a step back and go, look, there's complexity, yes, when you get down to local level, small time periods. But take a step back. Look at the big picture. We can indeed, I think, say with certainty that human beings are causing climate change. So, is the climate changing? Why, yes, we've seen this temperature record before. Is the change significant? And I think many of us in this room have contributed records. The Arctic is well represented now in updated versions of this. This is the temperature record now. We have time going from the right and back in time to the left, just to make sure you're paying attention and staying on your toes. We see that over the last 100 years or so, in 2 steps of warming, one that we think is pretty natural, the other thing is human-driven, that temperature has risen out of the bounds of any time in the last 1,000, maybe even 2,000 years, although the 2,000-year time period is certainly less certain. I'm interested in this not only because, well, I'm interested in this actually for one basic reason. It precipitated a fight, all right? There were a bunch of people who took a look at this and said, you know what, I don't like this, and for political reasons, I'm going to challenge this. I'm going to say that this is wrong, that were mistakes made in the mathematics or whatever, not really challenging the basic science behind the fact that the globe is warming and that humans are causing it, but challenge the basic sort of the little details, if you will. All right, that was to me, and for those of you who know about this, what was called the hockey stick controversy, where Michael Mann and some other folks got dragged in front of Congress and asked about statistical methods. By the way, it was the first time I heard the word paleoclimate spoken in Congress, and it was spoken several times by a bunch of people who really struggle with the word, but at least they got it. All right? This was very clearly, I think, the sort of the crystallization, certainly in my mind, that this is not really a scientific debate. This is a political fight, and if you fight it in terms of science, you're going to get killed. Right? It's a political and economic fight. How does it work? You seed doubt, you obfuscate, you distract attention, and this is an attention distractor. It doesn't really matter whether or not we're warmer today than we were 200 years ago, or 500 years ago, or 1,000 years ago. In terms of the physics and chemistry of global warming, it really doesn't make any difference whether you're coming from this baseline or that baseline and going up. Right? It simply doesn't matter. But if you focus on details that really aren't central to the point, you can divert attention. And that is really what was going on here. Oh, by the way, there are some of you in this room who share this wonderful title of junk science. If you go to junkscience.com, I know some people have computers on right now, go Google. You can find several people in this room listed under junkscience.com, and you ought to be damn proud to be there, all right? So, who's winning in this political fight? All right, again, science is informing policy, but it's really a political fight. And I think the answer comes through a number of polls recently. A Time ABC Stanford poll came out that agreed with a lot of other polls saying that roughly 85% of Americans say that global warming is happening. They're right. I don't know what the other 15% are thinking, but 85% of them got that right. 65% think that scientists disagree fundamentally about global warming. That's wrong. All right. In other words, those who are trying to seed doubt, obfuscate, etc., have won to a large degree. They have managed to divert attention from the fact that global warming is real to saying we scientists don't really agree, and so we really can't do anything about it. All right? This is an interesting battle technique. You could see that in the rest of the poll. About 81% of people oppose higher taxes on electricity. I think 81% of people oppose higher taxes, period. Or maybe 80%, so we gained one. I'm being facetious. 68% oppose higher gasoline taxes. In other words, we have a problem, but we don't need to do anything about it. And we don't need to do anything about it because the pesky scientists disagree. This is a perception and reality problem. To me, I talk about this in terms of alcoholism. Unless you admit you have a problem, you're going nowhere. Right? And it's coming to that realization that you have a problem is so painful, but it is absolutely essential that we do that before I think this world really gets its collective act together and starts doing something about it. Wonderful example, living on a fault line. A number of studies were done about people living in California, where, like apparently here, we have earthquakes. They asked people, how close do you live to a fault line? And of course, if they lived, a mile or a couple of kilometers, they said 10 kilometers or 5 miles. All right? So they consistently got it wrong, and they overestimated how far away it was. What was really interesting to me about that study was they broke down the responses by whether you had a high school education, no high school education, high school, college, PhD, etc. The PhDs and the people without high school education and everybody in between were the same. It didn't matter how much education you have. You were capable of looking danger in the face and ignoring it completely. For those of you who love the Hitchhiker's Guide to the Galaxy book series, you know that there are spacecraft landing outside all the time, and we just walk by and ignore them because this is inconvenient for us. Right? Same thing happens with earthquakes. Same thing happens with global warming to some degree. How big are human impacts? Simply put, we're the biggest cause of change on the planet. We already know that we've altered the Earth's energy balance. We've heard this today. We heard about sulfate today. We make more sulfate than all the phytoplankton in the ocean. That's the natural source of sulfate. There is a lot of phytoplankton in the ocean. And this is the one that really knocks my socks off because in terms of the energy, I know this is very impressive in terms of energy balance, but I think anybody can sort of wrap their mind around this one. We make more fertilizer than all bacteria in the world. So the natural way that nitrogen in the atmosphere, which is unusable by plants, gets utilized is to have it fixed in terms of either ammonia or nitrate and made available for plants, and that keeps the planet green and everything going. We human beings now take as much or more N2 out of the atmosphere and make fertilizer out of it than all the bacteria in the world. And that, to me, is just plain impressive because I can't even begin, maybe Ross can, but I can't even begin to wrap my mind around how many bacteria there are in the world. That's an impressive number. I want to back up for a second. This is a picture produced by Keynote. It's basically photographs of the planet put together. I have my students in my introductory classes, 340 bright, shining faces. I have them print this out and paste it on the wall across from the bathroom toilet so that every day, at least, maybe, they stare at this thing. And eventually it drills into your head, that all these white lights are human beings. They're all using fossil fuels, and they're all producing these greenhouse gases that are causing climate change. And they're giving us a reason to go drill ice cores and do wonderful things like that. What I don't like about this is that you can actually see the continental outlines because they made it kind of a lighter purple against the black. So this is the reality picture here. This is an older photograph composite. And you don't need the continental outlines to see Europe. You don't need to see Japan over here, North America. Oh, and by the way, you know, the wonderful aurora borealis tootling away up here. This is our Earth at night. All right? If aliens are flying by and wondering whether or not there's intelligent life on the planet, the answer is yes. It takes intelligence to do this, all right? Just for the, you know, just to make this Americo-centric here for just a second. It's moving on me. I love this because you can, we put in our interstate highway system after World War II, and you can begin to see actually the impact of the interstate highway system on the U.S. at night. You can see the. All right, what are the impacts of climate change? This is a question of ethics, economics, and politics, but it's all informed by science. We play such a key role in feeding information into this system. All right? Now, the economists are going to chew this stuff up and spit it out. The politicians and the policymakers are going to chew it up and spit it out. And the ethicists, slow to the game in my opinion, are eventually going to chew this up and spit it out. It's their responsibility to do all that. It's our responsibility to give them the information to chew on. Knowledge is key. All of these people need to know these two questions. What are the risks and what are the benefits? All right? And global warming is no different than anything else. We've got to analyze risks and benefits from an economic, from an ethical, sociological, all points of view. We scientists know that change always occurs on the Earth. We adapt. The big difference here is that human beings are causing this change. That kicks in that ethical point of view that really doesn't kick in. I mean, if we're all sitting here, if we were sailing into the next ice age, which, you know, we're overdue by a few thousand years if you look at the cycles of ice ages, we would, I think, be having a very different debate. We'd be talking about how do humans adapt to this natural. We wouldn't be talking about adding CO2 to the atmosphere, trying to engineer. I doubt we would be. Maybe we would. I don't know. But we'd be viewing this thing fundamentally different than we do today. We view it as a problem in large part because we are causing it. And if we're causing it, that gives us some pause in terms of what we're doing. Which leads me to two slides. I won't kill you on ethics, but I want to give you two slides on ethics. One is intergenerational ethics. And I have several graduate students that aren't I fund them, but they're not my graduate students, who are studying environmental ethics. And I find it fascinating to sit down with them and learn about this stuff. It's great when your graduate students know more about their topic than you do. So actually learn something here. Keep in mind that this increase is exponential. This is that CO2 plot I showed you again. And you can pull out some really surprising numbers. Half of all the atmospheric CO2, in other words, half of all the greenhouse, half of all the fossil fuels that have been burned were burned since 1975. How many people in the room can remember 1975? Oh, come on. See those hands? Some of you are not raising your hand, and I know you've seen 1975. The baby boom generation, you're out there, will burn nearly all of the oil and the natural gas. By the time we're done, we will burn almost all the oil and natural gas in one generation. Right? It was started earlier than the 1950s, but given the power of that exponential, we are doing almost all, 90% of that burning will be done by us. We will pay little of the environmental costs unless we get our collective act together and start to take that R word, that responsibility word, seriously. Right? Is it fair for us to leave our children and grandchildren with this legacy? That's intergenerational ethics. Other branches of ethics look at fairness across economic divides, rich and poor. The rich may have the money to adapt to climate change. And I say may because we'll talk about some of the nastier parts of climate change. We may have the money to adapt, but certainly the poor do not. We've seen this in a number of cases. Sea level rise and storm surges in Bangladesh are already causing people to move away from the coast, already causing damage to homes, and that's with inches of sea level rise. When we talk about 3 feet of sea level rise, which I think is a good estimate for 2100 or so, we are talking about 30% of Bangladesh. Right? Those people have got to go somewhere. And India May or may not welcome them with open arms. We don't know. I mean, hopefully we'll all get to be a whole lot friendlier because we're going to be living on less landscape. Right? Now, you also see this within the U.S., within industrialized nations. We saw in Hurricane Katrina what happens in the gulf between the rich and the poor. The rich were able to get out. They had cars, et cetera. The poor did not. Public transit wasn't running out of town. They ended up in the Superdome here. They ended up wandering through water up to their neck, and in many parts of New Orleans are still abandoned and not likely to be rebuilt anytime soon, although one could debate the wisdom of rebuilding New Orleans. Okay, I want to take briefly a little tour through impacts here, and I'll finish up hopefully with plenty of time for questions, because a lot of these impacts we've already talked about. I want to give you my little personal perspective on them. The expensive impacts, and this is my personal list, and at the end of my talk, if you guys want to jump in and let me know what your list is, I'm more than happy to talk about that. The expensive impacts are sea level rise, and if you talk to economists and ask them, should we mitigate sea level rise or should we adapt to sea level rise? They will ask you how much sea level rise. And in the back of their heads, they're thinking maybe 5, 10 inches. You know, the IPCC report currently says 20 inches by the end of the century, which ought to scare them a little bit, but it doesn't scare them. Right? When you say 3 feet or more, the answer changes. Then they will, I mean, I have friends, really friends who are economists, and they will actually go back, redo the calculations and say, boy, you know, it costs too much. We should probably mitigate and not adapt to that kind of change. Abrupt climate change is the other one, and there's a wonderful Academy report put out on abrupt climate change. Personally made my life a whole lot easier. I used to give talks on abrupt climate change, and people would laugh at me, and now they snicker. Anyway, this is another, the economists took a look at abrupt climate change and realized that we don't want to adapt to that. It's too expensive. Speed of change is important, and we'll talk about speed of change in a second, but the faster things change and the bigger the change is, the more expensive it is. The harder it is to move your agricultural areas, to move your industrial areas, and we do have to move industrial areas because you may lose the precipitation, the fresh water you need for cooling, for manufacturing, et cetera. So you have to move all the important parts of society, and that costs you a lot of money. And finally, this is growing, and get it out there, folks, because Arctic carbon is one of those nasty feedbacks that makes solutions harder and more expensive, and I'll come back to that. I think this is maybe, in the end, one of the real killer problems that we have with global warming. We've talked about this many times today. Sea level rise is rising. Sea level rise is rising. Sea level is rising and will continue to rise. Certainly, it's thermal expansion, mountain glaciers, maybe a little bit of Greenland, maybe a little Antarctica. Hard to tell on the big ice sheets right now. Wonderful paper by Stefan Ramstorff. Raise your hand if you read that one. All right, read it. Elegant. Comparison of temperature, global temperature, and global sea level rise, both measured over the last century. Build in a little lag for how sea level is going to respond thermally to atmospheric temperatures, and you find that there's an excellent R squared of 0.88 relationship between temperature on this atmospheric temperature and sea level rise. What that tells you is that thermal expansion is real, that it's happening, but it also scales for you the impact of that. Impact of thermal expansion and the melting of the small ice caps. The scaling that he gets with that, by the way, if you then put in the IPCC projections for temperature increase to 2100, he comes up with a sea level increase of about 3 feet, about a meter. Right? That's without any fast feedbacks. That's without the kind of fast feedbacks that we've seen here in Greenland and in Antarctica, where surface water manages to bore its way all the way down through the ice, lubricate the ice at the base around the coast, and speed up. For those of you who've been to Jakobshavn and some of these glaciers here, these things are dumping out very rapidly. There's a huge positive feedback as those melt ponds bore their way down, lubricate the base of the ice sheet, and start to get ice moving. Without that, we're looking at roughly 3 feet. If we get those fast feedbacks, we may be looking at even more. And that, as we'll see in a moment, is scary. We know that with the last time the Earth was warmer, about the last interglacial period, roughly 140,000 years ago, that sea level was about 3 meters higher. We have pretty good evidence for that, actually excellent evidence for that. The Greenland ice cap was probably smaller. This part of it down here was probably not there, although we have a lot of debate about that among glaciologists, but we think that's where a lot of that 3 meters came from. But we know that sea level was about 10 feet higher than it is today. Now 10 feet, and I'll show you in a minute what 3 feet looks like, but 10 feet is a lot of sea level. If that's where we're going, then we have huge impacts on the system. Hopefully you've all seen these. There's a number of websites you can go to look at and do your sea level games here. I just want to point out a couple of my favorites. This is the USA, Florida here, and I'll tell you in a minute why I picked this one. Here's today. This is with 1 meter of sea level rise. You see pretty much the Florida Everglades are gone. The United States is spending a lot of money trying to fix the Florida Everglades. Right? We spend a lot of money trying to fix things and then watch them go away. What I find fascinating about this, watch the Jacksonville, I think this is the Jacksonville River. Anybody here from Florida can correct me? St. John's, thank you very much. Winding its way down towards Orlando. So Orlando becomes a seaport. Now this is important because clearly what this means is that Disney is behind global warming. Right? Keep that in mind. I think you heard it first here, right? With a 3 meter sea level rise, which is what it was with the kind of warming that we're looking at, there's always a lag time built in here, so maybe a couple hundred years from now, this is what Florida will look like. And you see the Everglades are gone, Miami's gone, or it's not gone, it's underwater. Tampa's in trouble, and the cruise boats are now regularly cruising up the St. Johns River to Walt Disney World, which is high and dry. Right? The other example I want to give you, I'm not giving you this because of New Orleans, but because as a child, in every country, one of the first things you learn to do in geography is to draw your country, right? And if you're lucky, you live in a country that is relatively easy to draw. I had to draw the Gulf Coast repeatedly because I couldn't get that darn little Mississippi Delta right. And, if nothing else, my grandkids or great-grandkids won't have to draw the Mississippi Delta anymore. You got that working for you. The other thing to note is that Baton Rouge becomes a coastal town. Right? So if you want to know where to go to buy nice oceanfront property, Baton Rouge might be a good place because it is up on there's a ledge here. All of this is the Atchafalaya Delta, the Mississippi Delta. There's all sediments in here. They're going to sink and go underwater anyway. So this is where to buy your new beachfront property. All right, abrupt climate change. So sea level is a big problem, big economic problem. The other big economic problem is abrupt climate change, in my opinion. Right? This is, if you look at the history of, again, paleo world here. Oh, and I cheated. There is no scale on the bottom at all. It's depth, but there was supposed to be an age scale on the bottom, but it got peeled off. Right? So anyway, this is roughly about 8,000 years ago. That's 8,200 years ago right there. This is the glacial period, so this is around 140,000 years ago back here. It's mostly the glacial period we're looking at here. The nature of climate change in Greenland observed over and over again, which we also observe in North Atlantic sediments and in Cariaco Basin and Santa Barbara Basin. We observe around the world, nice records from Europe, from Russia, everywhere, China, not everywhere, but certainly most places in the Northern Hemisphere, is that climate change, at least during the glacial period, was a very abrupt creature and a very big creature. These are changes that are, my pointer's dead, these are changes that are roughly the size of glacial and interglacial kind of changes, and they happen over very short periods of time. How short a period of time? We can take a look here. So this is a blow up of this last one right here. One of the first things that I got to do as a fresh PhD was I had the honor of working with Willy Dansgaard and Sigfus Janssen, and we went in and we took the Die-3 ice core and cut it up into yearly bands, which we hadn't thought of to do before. But we cut it up in yearly bands and measured year by year what temperature was doing. And so if you take this little piece right here, you blow it up, and you get this. This is the isotopic composition of ice, which is a proxy for temperature and for other things. We didn't know quite what other things. But you see this high variability and the rise here. And the rise, this is now on a time scale that you can date because you can actually measure the annual layer thickness by a number of mechanisms in this ice core. So roughly 12,000 years ago, you can say that there was a warming. It was about 10 degrees, 12 degrees Celsius. It occurred in about 50 years, a human lifetime. So my nice little story here that I tell my students is that, yes, there was a time, a real time in history, when a father said to his son or a mother said to her daughter, when I was your age, I used to have to walk to school through snow, uphill both ways. It actually did happen once, all right? And I suspect that, and Igor can help me with this, maybe this is gone down through the years, perpetuated itself down through the years. Okay. I don't think so, but that's worth a beer, Igor. One question we had at the time was whether or not this was noise, or whether this was signal. Here is the GISP2 core on top of the North Grip core. I don't even show you the Die3 core. I could show you that on top. You get several curves together. It's harder to see. But you can see that, again, 2 cores dated totally separately, isotopes measured. You throw one record on top of the other. We're not looking at noise here. We're looking at a very prominent signal. Even some of the details in here in terms of, for example, when this thing kicked off, it went up by about 5 degrees Celsius, probably in 3 or 4 or 5 years. Plateaued for a while, oscillated around, and then shot up by another 5 degrees. So there are thresholds in the climate system where you can have a temperature change of 10 degrees Celsius in 50 years. And within those thresholds, there are mini thresholds where you can have temperature changes of as much as 1 degree Celsius per year sustained for 4 or 5 years. The Arctic today is getting close to that kind of temperature change. We saw that today in one of the talks. Globally, we're looking at temperature change maybe 1 degree Celsius over 100 and something years here. So the kind of changes that you see here are much faster. All right? 1 degree per year versus 1 degree per 100 years, 100 times faster. In the Arctic, it's not true. The Arctic is speeding along at a much higher pace, but these are really big. These are what we call abrupt climate changes. We haven't really seen one of those in our lifetime, certainly. This brings me to another plug here, the International Partnerships in Ice Coring Sciences. We want to go back and look at the last interglacial period in Greenland with the same kind of detail that we did in that Die3 record. We want to look at that last interglacial period, try to find out what was happening around that time period. We haven't been able to grab that yet in a Greenland ice core, and I want to show this because it plugs Dorte Dahl Jensen's talk tomorrow on the NEAM core. So hopefully you'll all be here to catch that, and the plans to drill a new deep ice core in Greenland. So are there thresholds in our climate system? This is the big, the multi-trillion-dollar question. Are there thresholds in our climate system? The ones that we can point to right now are certainly sea ice. We've heard about that a lot today. Ocean circulation. We've heard about that a lot today. North Atlantic Deepwater Formation. And atmospheric circulation. All right? I want to come back to this in a second. The sea ice issue is a one that we've seen over and over again. This is not my slide, but this is the one that I stole. You can see the amount of sea ice extent, particularly in the summertime, decreasing. We've seen much better talks on this. I won't dwell on it. I do want to point out that sea ice thickness is decreasing. And this, I think, is really important. If you go and you look at ice, ice is a very nonlinear creature, particularly as it melts. It doesn't just, you get holes in it and it stays thick. What happens is it melts from the bottom, melts from the top, and gets thinner and thinner and thinner until it reaches a thinness that, as we heard from the indigenous people, it can break up quickly or it can form quickly. All right? So there's an inherent nonlinearity in sea ice that I think we really have to keep an eye on. It's not just a question of when the Arctic is ice-free. It's a question of how rapidly the Arctic goes from an albedo-rich reflecting surface to a blue ocean or darker surface. How quickly does that happen? If you watch lakes melt out around here, you know when spring comes, and these lakes are, they have ice on them, and it seems as though maybe in a couple of weeks, the ice goes away. It's not as if it takes months for this to happen. It happens relatively fast. if the same kind of processes happen with sea ice, and no guarantee that it does because we're looking at different scales here, then my point is we need to consider not only the extent of sea ice, but the speed with which sea ice can be removed. Something we've also heard about here is ocean circulation. This is the deep water formation. Will we have these areas of deep water formation that can form deep water, helping to pull warm water up north? This is, as we heard previously today, may cause a cooling, certainly be overwhelmed eventually by the warming caused by greenhouse gases. One of the important points that I want to make here, I've been working for a while with one of my postdocs, Jacqueline Flugaker, who's going back to Switzerland in about 2 days or so. We've been running models, everybody runs models, to try to understand how this North Atlantic deep water formation functions and how things change when it no longer functions. Interestingly, a lot of the fingerprints of North Atlantic deep water shut down we see in the models, we also see in the ice cores and in other records. The one thing that the models don't get right at all is the speed with which this happens. I showed you the records. The speed with which things change are years to decades. The models take centuries and maybe even longer to have the same kind of change be affected. So there's something missing in the models. And that makes me nervous because I think the models have the basic idea right about what happens when ocean circulation changes. I don't think they have, as a matter of fact, I know they don't have the speed right. And the speed, again, is critical. The faster things change, the more expensive it is to deal with them. So this is one thing, even though I'm still nervous about this shutdown of deep water formation. What effect would that have on the system? How rapid would that change be? And therefore, what kind of impact would it have? Abrupt changes are what we call adaptation killers. It's cheaper to mitigate than to adapt. I've said this before, the faster, the larger the changes, the more it costs to adapt, the less likely you are to adapt. One important thing is, and I said this earlier, keep in mind that the pace of change is increasing exponentially. As population goes up, as energy use per capita goes up, CO2 levels are rising. We're on the steep end of an exponential, folks. We know this is true. The time between when we see a problem and when we need a solution is shrinking rapidly. You add abrupt climate change on top of an already rapidly changing system, and I think you have the recipe for trouble. All right, just a quick comment about feedbacks. This is the Arctic carbon. We just heard a wonderful talk Vlad gave about the Arctic carbon. The amount locked up in Arctic carbon is impressive. Number of estimates have been made in the literature, roughly equal to the amount of all fossil fuels. Is about a decent scaling, I think. Now, it stays there because it's frozen. Vlad set that up wonderfully. Will it remain frozen? Not likely. He showed a different version of this. The poles amplification of warming is very marked, and so these areas are warming much faster. This is actually his slide, and you can see that the temperature of the permafrost is rising. We have seen a number of studies, including one from his colleagues up at UAF, Katie Walter, et cetera, showing that you get these bubbling of methane out of these melt ponds. This is a real problem. And I'll mention why it's a real problem in a second. I just want to point out that I study the atmosphere. I study CO2 and methane in the atmosphere. We have not seen evidence that this polar carbon is being released in large amounts yet. We don't see it. I fully expect, as a matter of fact, we've written proposals to go and observe this. And of course, people say, well, you got to have a problem before we want to fund this. So anyway, I won't go deeply into that. But the monitoring of carbon fluxes is ongoing. I don't think we're not nearly enough sites. We've got some good permafrost sites here. We have a few over here. Unfortunately, a lot of those Russian permafrost observations are offline right now. In terms of the atmospheric monitoring, I don't think we have nearly enough sites as well. This is a huge problem, and we are not putting anywhere near the resources into monitoring that we should. This is, I think, what we need to do in IPY, build up that Arctic observing network. We need to add to these sites because we don't have nearly enough sites here to do a good job of monitoring this. Now, here's the problem, I think, with this Arctic carbon. It's not just a problem because it can increase greenhouse gases in the atmosphere, but even if we had aggressive carbon dioxide and methane mitigation, if we went at it whole hog, the planet's still going to warm up. And as the planet warms up, if this stuff starts to come out of the ground, then you run into a serious policy problem. If policies don't have tangible outcomes, it's very difficult to maintain them and very difficult to implement them. So if we start to mitigate, actually sequester carbon out of the atmosphere, and yet we still see carbon coming into the atmosphere, then we've got a policy problem. Getting the political leaders and getting the people behind us in such a situation is very difficult. These natural feedbacks create fundamental problems for us as scientists and create huge problems for policymakers. So there's a little nugget to stick in your head there. All right, final slide. The Anthropocene is here. I've looped back to Armin's talk earlier today. The rules have certainly changed. The pace of change is increasing. The time between when we recognize we have an environmental problem and when a solution must be found is shrinking to very, very small. All right? We don't have the luxury anymore of debating whether or not an environmental problem like climate change is real or not real. We need to quickly throw out the garbage, assess the problem, and we as scientists, the only way that's going to work is if we as scientists learn how to communicate better with policymakers that which we know, so that they can apply their filters in their heads for when the people come up to them and say, no, these scientists don't know what they're talking about. Right? Scientists do know what we're talking about. If there's anybody on this planet who know what they're talking about, it's scientists. And I'm not just buttering you up. That's what we do. Knowledge is our business. We throw out the crap. We keep the good stuff. Knowledge is our business. Don't forget that. Educate yourself about these problems. Educate others. And take responsibility. And I'll stop there and take questions. Oh, okay. Don't tell me I didn't annoy anybody. Yeah.
I'll stand. First, thank you for a really energetic talk. That was great.
Well, it's pre-beer, so we got it.
Secondly, just to feed on all that energy, because I know I just want to put in a pitch for tomorrow. We're supposed to talk about ideas for working together, and there's a lot of program guys here, so that's a really good idea. And with what you're saying, if I wasn't a scientist, I'd probably panic and go out and buy some high ground in New England somewhere to be safe. But since I am a scientist and I own high ground in New England, I'm already at the next level where I say, how do I participate in the responsibility part? And one thing I have found in trying to do my science is that I'm also an engineer and a biologist, a polar oceanographer, a few other things. But as I try to pursue solutions, I often find myself caught with the funding cycles of trying to fund an engineering solution to solve an operational problem so I can do my science. And maybe that's a good thing for this venue to consider is how do you create funding mechanisms for an engineer to work with a scientist, to work with a policy person, to solve a solution, and how can a scientist or anybody write grants to try to get money to look at these problems? Because the problems you're showing are incredibly interdisciplinary. Networking systems require granting mechanisms that are not available right now. And operational people do not have the same kind of monies or capabilities of monies to talk to that scientists do. And with all the energy you just threw in there, I could just see that as like the next step. So this is either a pitch or a ploy or to encourage or to build on your thoughts, but do you have any comments on that from your current experience?
2 comments, and I'll be brief. One is I want to praise the National Science Foundation for the IGERT program. Because if you don't know about it, know about it. All right? We had an IGERT grant at Colorado. It changed the way I look at my science, because I got to work with policy people for 6 or 7 years. I got to work with journalists. I got to work with lawyers. I've got a graduate student who is getting a degree in business and going out and starting green business. And on that person, I'm pinning lots of hope for funding my research in the future. So learn about the Igor program. It's a wonderful opportunity. It addresses the interdisciplinarity of education. The second thing I want to point out is, as I pointed out here, we need to be agile. I think the mechanisms by which we fund things, I think, are already pretty good. But we need to be very agile in terms of recognizing when problems pop up and saying, hey, we got to deal with that. We've got to jump on that one in a hurry. All right, because the time between when we see a problem, like, say, Arctic carbon starting to come out of the ground, boom, we got to jump on that. If we don't have 1,000 boreholes for permafrost, we better get them out there, and we better get them out there in a hurry. We've got to be agile. Bob.
I'm wondering about the emphasis on CO2. As if you had no CO2 in the atmosphere, you would radiate energy through that wavelength. As you add CO2, you start to absorb the energy that radiates at that wavelength. And at some point, you've added enough CO2 so that it's essentially opaque. And any more CO2 that you add doesn't have any cumulative effect. And I would suspect we must be at that point. And is that the case? And so adding, my question is, why is there so much emphasis now on adding more CO2? It should be the other greenhouse gases where there's windows that are still open that ought to be maybe more attention paid to.
Well, just a couple of quick comments. We can talk about this offline. I agree with you that the other greenhouse gases really need more attention. If we were to get very serious about coal, oil, and natural gas and sequester all that CO2, those other greenhouse gases are going up. They're already equal to CO2 cumulatively in their radiative impact, and they're growing quite rapidly. So we have to keep our eyes on those things. The second point I want to make is that CO2 levels, we know 55 million years ago were maybe 1,000 ppm, and the temperature was proportionately higher. So whatever that mechanism is still, there still seems to be that relationship between CO2 levels on the planet and temperature of the planet, even back to probably 1,000 to several thousand parts per million. Now, we need to do the radiative calculations to figure out, how much sense that makes from, a saturation point of view with CO2. And that's a discussion we can have that these other people probably won't get excited about. Jack.
I thought that your comments on discussions with your students about the ethical dilemmas and the impacts of this were very interesting. But you made the point that you can talk to economics folks, and there's certain thresholds where they start to take it seriously. But what are the prospects, or what can we do, or what is your impression about getting some non-standard economic metrics in there, like the rest of the biosphere? Like, that's not figured in. The difference between 1 foot and 3 foot of sea level rise may be important for people that are ensuring developments in Miami. But what about the rest of the biosphere that may be in depot longer?
I think that's coming, and it's coming very rapidly. Natural resource economics is a growing field. And again, we can talk about that over beer, but the field of economics is slowly evolving, probably certainly slower than geosciences, slower than what we do, but it is slowly evolving. They're beginning to incorporate the costs and benefits of ecosystems, et cetera, into their models. So they're not ignorant of this, but it's taking them longer to feed that into the system because basically the way that they reward good economists does not include any of that stuff. And we've got to change the reward structure. Yeah.
I just want to comment that I think there's a connection between the question about how you fund these sorts of interdisciplinary projects and this Jack's comments. And I think the issue is partly about how universities are structured. Universities have all the resources necessary to tackle grand scientific problems or grand social challenges. And we're not doing that very well because of the way universities are structured with discipline in a box, discipline in an edifice. And I think the responsibility is not all on the funding agencies, but partly the responsibility goes to universities to start to restructure themselves because the funding agencies respond to pressure. If universities stop building these tall edifices and start to rethink how to leverage the fantastic array of resources they have, then we'll make a lot more progress.
Amen. Couldn't agree more. I spent a decade at the University of Colorado building an environmental studies program that has social sciences, natural sciences, humanities. And I think, the NSF, for example, is ahead of us, university-wide. And I agree with you. Couldn't agree with you more. Love you. Yeah.
When the whole climate change business started, I felt that politicians took an attitude that, yes, this is probably a serious problem, but we don't really want to do anything about it, but we want to be seen to be doing something about it, so we'll put money into research. And that fed the argument that climate change was a hoax perpetrated by climate scientists to get more research money.
Yes.
Now I'm seeing that politicians are saying, yes, this is a really serious problem. We understand the temperature is rising. We're going to spend lots of money on mitigation. We're going to spend lots of money on adaptation. But since it's a known science problem, we don't need to do any more research. Any reaction?
There is a reality to that. That once you have defined clearly enough the boundaries of a problem, we're not going to get gobs of money to do research in that area because the politicians feel as though they're going to implement something. So I think that's a reality that we as scientists have to face. Now, one still does science based on curiosity and based on a general mission of trying to understand the planet. And we can make very good arguments, I think, to our funding agencies around the world that, look, if we quit looking at the planet, we're going to miss abrupt climate change. We're going to miss Arctic carbon. We're going to miss a lot of those things that we're on the edge of trying to understand. Clearly, we still need to understand our planet. If nothing else, tell them, look, the goal is not climate stability. The goal is sustainable societies on this planet. And climate is only one piece of that. We're talking resources, water, population, everything. If we don't understand our planet, then we don't really reach that important goal of sustainable societies on the planet. And we got a long way to go to do that. Maybe there's some time when scientists begin to taper off because we understand enough about how things work. Fine. I'd love to get to that point. We're not there now. We done? Yeah.
Some of us have read the paper where they're talking about people like you that say, oh, the sky is falling, but it's not falling. So that made me so angry that I'm going to write a letter to the paper, an editorial. And when you said educate others, I think that's what we're trying to do.
I agree.
And I feel that maybe the Wall Street Journal and Fox News needs to be educated because I think they're in the pocket of people who say the scientists are not right, that the sky is not falling.
Yes. Jack?
This is surely a very impolitic point, but you got us all inspired. Take responsibility, cost-benefit analysis. I want to leave the charge to all of you who flew here. Your environmental impact was huge, so let's do some good brainstorming and get some outcomes in the next few days.
Well, and if I could just jump in for a minute, there is a group of people here who are very important. The World Meteorological Organization, Jim Drummond, the Canadians, who rarely get together, and they happen to be in Hanover now. So at 6:30 tonight, if your name is Len Berry, Jim Drummond, Paul Shepson, Jan Bottenheim, Jack Dibb, atmospheric chemists, go to the Canoe Club to discuss the International Arctic System for Observing the Atmosphere.
We talk to other people as well.
You can bring them in. Yeah. Go ahead.
You want to get that question?
Oh, yeah.
Can I ask another question?
Yeah.
Yeah, so, my view is that one of the reasons that the world, people who write letters to the Wall Street Journal are arguing is that the message is very depressing, very negative. And I think that we have to work really hard to keep the message more positive. And I think there are easy ways to do this. And we have a fantastic challenge. And it could be exciting to use the resources of the United States, which obviously are excessive. We have lots of money to blow. and we're not doing it. So I think we could have a positive message, and we could be leaders, and we could do something great. And so I think we need to work a little harder, and I'm wondering if you have any thoughts about how to communicate in a more positive way, rather than trying to convince everyone that the sky is falling, because it is. Okay, so let's move on.
Well, two quick thoughts. One is there's an I in IPY, and I think if this isn't a global solution, we are in trouble. And we've got to have that international cooperation. This is not a U.S. problem alone. This is not an Icelandic problem alone. This is a global problem. And let's grow up and deal with it as a global problem. The other thing I want to say is I agree with you. It's a challenge. And, I teach a course. I think we all, not all, many of us teach courses like this. And you stand up in front of the students and you just kind of pound them with this stuff week in and week out. And it gets a little down after a while. To me, I always come back to solutions. And, you stand up in front of a room of 300 and something bright, energetic college kids, and you just can't help but be enthusiastic about your future. Because, human beings are wonderful creatures. We have excellent minds. We can deal with these problems. But, like those alcoholics, until we recognize we have a problem, until we're willing to bust ahead and deal with it, we're not going to do it. But I think when we do recognize we have a problem, we're going to do wonderful things. I think we're going to have economic growth. We're going to have all sorts of wonderful things.
One more?
One more, because there's beer somewhere.
You've been talking about beer.
Yeah.
I don't want to take you long. Yeah. But just to try to put another spin on things or another take. The Anthropocene starts in the middle of the 18th century. That's 1750. That's when he dates it. Call it roughly then. That's when we start really, that's when Watt is perfecting the steam engine and we're starting to use fossil fuels. We're getting ready. It's at that time that the word civilization is invented. We had no word for civilization until 1757. We talked about empires and all the rest. I could track this further, but I would say the problem we face fundamentally is civilization. It's us. And it would seem to me the problem is also ethical, and you're right to talk about it. There's something unethical about the way we set ourselves up. And I think in the case of civilization, fundamentally we are going to town on nature. We're having a high life, a good time on nature, and somebody else is going to pick up the bill. It would seem to me the value of science, that is natural science, is to tell people that there is a moral and ethical problem they have to face up to. But I think swiftly got to move into this other dimension you're talking about. The moral order has to be changed. And that's a hard thing for people to take when they want to actually climb. Anyway.
I'm struggling to remember who said it. It's a wonderful quote that we're running the earth like a going out of business sale. Al Gore? Somebody, is it? We done?
Okay. And I thank you.
Thank you.
You're welcome.